we present the Aerial Gym Simulator, an open source framework that extends NVIDIA Isaac Gym to enable highly parallelized simulation for multi-rotor platforms. The simulator architecture demonstrates our modular approach. Various submodules for robot control, rendering for exteroceptive sensor data, and environment randomization are tightly coupled with the underlying physics engine. Our framework significantly advances the state-of-the-art by supporting diverse robot morphologies, including under, fully, and over-actuated configurations, along with multi-linked airframes incorporating both reconfigurable active joints and passive soft joints. We contribute a custom rendering framework for GPU-accelerated raycasting. Environment entities are represented as triangle meshes that are transformed to reflect their updated states. A tensor-based API allows consolidation of image tensors, randomization of sensor orientation, and projection model, leading to greater control in simulation. Our framework allows us to go beyond the data types provided by Isaac Gym. Sensors with user-defined projection models such as 3D LiDARs can be simulated to obtain additional information such as surface normals, phase indices, and point clouds. Our implementation achieves an order of magnitude improvement in performance compared to the native Isaac Gym sensors for a large number of environments, significantly accelerating the training of exteroceptive sensing data-based policies. Parallelized geometric controllers are provided that imitate real-world interfaces, allowing tight coupling of learning algorithms with real-world robot controllers. We also provide a control allocation scheme for non-planar configurations to jumpstart training for arbitrary airframes. Out-of-the-box integration with deep reinforcement learning frameworks allow users to train and evaluate control and navigation policies using both states and exteroceptive sensor data. We conduct a series of experiments to validate the sim-to-real transfer of trained policies. First, we train a velocity yaw rate control policy for tracking a position set point for a quadrotor platform. Subsequently, an acceleration yaw rate control policy is trained for the same task and demonstrates a competitive real-world performance. Using the custom rendering framework, we train a depth-based navigation policy in simulation. The policy uses the robot state and a compressed latent representation of the depth image to successfully navigate a cluttered corridor and reach the goal location in a real-world experiment. Finally, we model the joint response for Morphe, a quadrotor platform with flexible arms. We further compare the performance of motor control policies trained for a rigid variant of the platform against a joint-aware policy trained to minimize joint oscillations. Thank you.